Okay, after we learned about the similitude law, now we would like to perform couple examples to illustrate how do we really build this similitude law which can bridge the models and the prototype. Now, the first example we will look at is a closed conduit. The pressure coefficient is a dimensionless one, as you can find from your previous common parameters. So you look at this one, the problem we see here is outside the engineering hall, there is a big constructions. At the 600 millimeter means what? The valve is 600 millimeter, 60 centimeter valve. To determine for the 5 degree of water with a maximum velocity 2.5 meter per second. This is a prototype. So can we use a smaller model which is 60 millimeter, 6 centimeter diameter, performing 5 degrees C is the same water? And what would be the required water velocity so that we can bridge this model and prototype? In order to do that, we will perform the Buckingham pipe analysis, which will end up with dimensional parameters. Length divided by d is the length of a pipe, diameter of the pipe. Epsilon is the roughness of the pipe divided by diameter of the pipe. Now rho Vd divided by mu is a Reynolds number. So in other words, this is the thing that we learned at the beginning of the class, Buckingham pipe method. Now we also learned about the similitude law, and there are a couple of them. First, we will use the geometric similarity. Means what? The model diameter and the prototype diameter. The ratio is 1 to 10. We need to follow these geometric similarities. Next, we will require the Reynolds number should be the same between the model and prototype. This is a requirement. And so in other words, the ratio is 1. In this one, the density is the same because we use the same water. Similarly, viscosity should be the same. So we end up with a relationship of Vm dm divided by Vp dp. Now, in the geometric similarity, we have 1 to 10 ratio. In other words, in order to have this one bridge between the model and prototype correctly, we will require the model velocity is 2.5 times 10 equal to 25 meters per second. They will reach the dynamic similarities between the model and prototypes. So this is the first examples. Now everyone suppose you should know how to do this kind of thing. First, we always develop the geometric similarity, and we require the dimensionless, particular dynamic similarity equal to 1 between the model and prototypes. And then we find the relationship between the model and prototype, in this example, for the velocity. Then look at the next example, immersed body. So now, this is the prototype, is airplanes. They fly 240 miles per hour. We would like to determine the drag force of a prototype. You will say, wow, how do you determine the drag force of a prototype? So instead of using the prototype, which is a real case, actual structure, now we build the small models, 1 to 10 ratio. We also require the models be performed in a wind tunnel, for example, 240 miles per hour. Now, if a model drag is 2 pounds, would we be able to determine the drag force of a prototype? Now, this 2 pounds is determined from a wind tunnel, which is easy, that you can use some kind of instruments, like a strain gauge, for examples. So, if you recall again, this will be the dimensionless Buckingham pipe method. In other words, pi relation, dimensionless number, Li and L is model and prototypes, and then epsilon is a roughness of the wings on the surface and the length of the airplane. Again, Reynolds number, dimensionless Reynolds number. So how do we do that? The first step is the same. We use the geometric similarity between the model and prototype, 1/10. Now, again, require the Reynolds number is the same between the model and prototype. In this example now, we will be able to obtain relationship of the model density and the prototype density. Keep in mind, the prototype should be at a very far away from the land, so the density might be a bit different. So in this example, that we have the length determined from here. Let's go back to the previous period. The length is 10 and 1. Velocity in this example here is a prototype, and Vm is 1. Now we will also select the viscosities M model and viscosity prototype is L, they are 1. So in other words, equal to 10. So we require the similitude law of the dimensionless for this example here is a drag coefficients between the model and prototype should be the same. So having said that, we will be able to determine the prototype of the drag equal to the model of a drag, and then following with the information we get from here. Now the way we get is 2 pounds is a model drag. Density between the prototype and the model is 1/10 now. Inverse of the previous relationship. Velocity of the prototype and the model is 1. The geometric similarity is 10:1. So if you follow this, it will be very easy to get the information about 20 pounds. So I believe that after these 2 examples, you might more or less know how to apply the geometric similarity and make sure the Reynolds number or common dimensional number that should be the same between the model and prototype. And the rest of it is following the question that you ask to move it left and right, eventually come up with the results. Let's do one more example to illustrate further on the similitude law. Okay, so this is a free surface flow examples. As you can see from the previous one, prototype spillway is 50 meters. Now we design the discharge, which means this prototype need to discharge, means this will release the 20,000 cubic meters per second water, which is a lot of water. So we can always do the real experiments, very expensive. Before we really build, we can always build it and then to see whether this one performs 20,000 cubic meters per second of the discharge. Or we can use some kind of numerical model as we learned from the chapter 6. Or we can use a physical model, which is what we are talking about today. Small physical model. For example, it will be fun to build a 50 centimeter models. And so how do we do that? The question is that we would like to see that whether the model flow rate, what is the model flow rate, will be the relationship between this model flow rate and the discharge, if we follow the similitude law. So again, we always go back to the Buckingham pi method. At the beginning, what we learned about how do we get this. Pi is equal to the relationship of Li and L, and epsilon is L, is roughness and the length scale of any of the prototype. Again, this is a new parameter called Froude number. If you go back to look at your common parameters. Another one we found is Reynolds number. And the last one we found is what? Is Weber number. So let's look at this example here. most of the time for the free surface flow, the most important thing that it usually dominates is gravity flows, because the free surface is not in the pipe flow, and gravity dominates. So in other words, we will choose this one as our main dominant one. Now if you look at the geometric similarity between the model and prototype here, 50 meters is a prototype, 50 centimeter is a model. So now in this example here, the ratio is 1/100. Now require the fluid number between the model and prototype the same. So in other words, we can move the velocity of a model divided by velocity of prototype equal to this relationship. The next one, because our interest is what? Are we able to estimate the QM based upon all of the similitude and between the models, which is what we want to know, and the prototype, which is a given. Based upon this simple relationship, we can get QM equal to AM VM. Now keep going on. AM can be expressed as length square. Now VM can be expressed as, if you follow from this relationship, of a square root of LM divided by LP, prototype. With this, you can come up with a ratio on LM 2.5 divided by LP 2.5, which we found from the geometric similarities. So in other words, if we can find that the LQM by this relationship, that means what? We will be able to get the prototype spillway of 20 cubic meter per second. So most of the time that people build the models, get a relationship of a model flow rate, then we can what? Even invertibly get the prototypes informations. That's how useful the model if we learn in this class. Of course, you can always use the similar concept to do in other area, like structures. Okay, so let's keep in mind we have 3 examples. This example is free surface flow. The previous example is immersed body. The first example is a closed conduit. I hope you review these examples and you will be able to do your homework easily. Okay? I will see you in the class on Tuesday.